Folks, this is the lesson for Unit 4, Lesson 9. And in this section, we're going to talk about a few different applications of exponents. The first one here is scientific notation. And the second one is going to be compound interest, which we've already talked about a little bit. So scientific notation is basically a way of representing typically really big numbers in a more compact way. So one of the examples here, this is it's called scientific notation because a lot of the time science deals with really big numbers or really small numbers. So for instance, a lot of our applications might come from astronomy and measuring distances in space or measuring the size or the weight of very large objects like the sun. So if we were able to weigh the sun, we would see that it's about this many kilograms. So it's a 2 with how many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30 zeros. That's a really big number, and it's cumbersome to write that out over and over. If you were trying to do math, nobody wants to have to write like 0, 0, 0, 0 30 times. That's not an easy way to do things. So what we're going to do is talk about a way to, let me see if I can scooch this down a little bit smaller for us. A way to deal with that really large number that is a 2 with 30 zeros after it. And we're going to look at multiplying 2 by different exponents of 10. And we use 10 because that's what each kind of row in our place value system, we use a base 10, like tens and hundreds and thousands. All of those are 10 times each other. So if you had, for instance, 2 times 10 to the exponent 1, 10 to the exponent 1 is just 10, so that would be 20. The next one down, 2 times 10 squared. We know that 10 squared is 10 times 10, which is 100. And 2 times 100 is 200. If we increase that exponent again, 10 cubed, this would be 2 times, what's 10 cubed? You could do it on your calculator with your exponent button, or in your head if you're comfortable with multiplying. 10 times 10 times 10 gives you 1,000. So what's 2 times 1,000? That's 2,000. And you'll notice that as we go down here, this is adding a 0 at the end each time. When we multiply it by a bigger exponent, every time we increase that exponent on the 10. So if I had this big huge number that has 30 zeros, that would be 2 times 10, and my missing exponent here would be 30. You would have to multiply a 2 by 10 30 times to add on those 30 zeros. So representing this big number up at the top, this 2 with 30 zeros after it, we can write that in an easier way. We can say that's 2 times 10 to the exponent 30. And that's scientific notation. It saves us from having to write out 0, 0, 0, 0 so many times after the number parts of a really big number. So we're going to try a few different conversions back and forth. So when we're using scientific notation, we are always going to have one digit to the left of the decimal. So we're eliminating all of the big amount of zeros at the end of a really large number. So if I were to look at this one, 256 million, so 256 with 6 zeros after it, we want to basically move that decimal point over so that it only has one number to the left of it. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8 times. So I'm going to write this as 2.56. And how many times would I have to multiply 2.56 by 10 to get back to my original number of 256 million? So each time you multiply by 10 is one step on that decimal place. It moves the decimal or puts a 0 at the end one time. And we have taken 1, 2, 3, 4, 5, 6, 7, 8 steps. So that's my exponent on my 10. And you can check that on your calculator. You can type in 2.56 times 10 to the exponent 8, and you'll get that 256 million. Some of our numbers, though, are going to be too big even to fit on your scientific calculator. So each time we're going to look at how many decimals we would have to move. How many steps does the decimal place have to take? So here, the number part that I'm looking at starts with 5345. So I'm going to have just one number after the before the decimal, 5.345 times 10, and I have to figure out my missing exponent here. How many steps would I have to move that decimal place to get back to the original? So if my decimal was here, we'll count the steps, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. So that would be my exponent on my 10. So each time you're really just looking at the exponent that you would have to put on 10, how many times you would have to multiply this decimal or this smaller number by 10 to get to the big number that you started with. And then the last one, what is this? This is 32,500,000. So I'm only going to have one number before the decimal, 3.25. And how many times would I have to multiply by 10 to get back to this big number? So there's where I've put my decimal like that, right? So there, taking that decimal place, and we'll move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So that's times 10 to the exponent 10. So every time you multiply, if you multiplied, say, this last one, 3.25, if you multiply that by 10 once, it would be 32.5. If you multiply that by 10 again, 325. Multiply it by 10 again, 3,250. So you're going to each of these 10s would make it bigger, bigger, bigger until it gets back to its original size. We're going to look at converting the other direction too. So if you have a number 7.045 times 10 to the 8, I want to make that into standard form. So 7,045, those are my numbers. Now I'm going to have to, every time I multiply by 10, I have to multiply by 10 8 times. And every time it's going to get a little bit bigger. So multiplying 7 by 10 one time would give me 70. That's where that decimal place would be. Multiplying it by 10 twice would be 704 with these decimals. Multiplying it by 10 3 times, 7 point something times 10 times 10 times 10, that would be 7,000. But I need to do this 8 times. So I need to multiply it again. I would get a 0. Multiply it again, another 0. So I'm going to have basically 8 steps here. And you would not ever really label these steps like this. 6, 7, 8. I'm just showing these like labeled numbers in red to show you how I'm kind of counting those steps. But you wouldn't have to actually show that on your work. So this will be 7, 0, 4, 5 with then how many? 1, 2, 3, 4, 5 zeros at the end. So that's 704,500,000. And then I'll do the same thing for the next two. You may want to pause this and give B a try, and then unpause when you think you've got it to check your work. Okay, so I'm going to start out with 9412, and I have to move this decimal place 12 times because it's multiplying by 10 12 times. It's times 10 times 10 times 10, 12 different times. So this is going to move it 1 time, 2 times, 3 times, but then I have to go still 9 more times. 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would add on 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, plus the 3 steps to get past those decimals. And then my final answer would be this 9412 0, 0, 0, 0, 0, 0, 0, 0, 0. So a really, really big number. What's that? 9 trillion, I think. And then the last one, again, you can pause this if you like, give it a try, and then check your answer. Okay, so I'm going to start with 3. I'm going to get rid of that decimal. 1, 8, and this would be 2 steps to get past those decimals, the 1 and the 8, but I have to go 8 steps on my decimal place. So I'm going to have 6 more steps after that. So I'm just going to add in 6 zeros and confirm that this is moving 8 steps. So 1, 2, 3, 4, 5, 6, 7, 8. So that final answer is going to be 318 million in standard form. So at the start, I said that we were going to look at scientific notation as a way of dealing with really, really big numbers, which the last ones were really large numbers, but also really, really small numbers. So we're going to look at a pattern with different exponents on our base of 10. And some of these exponents at the top should be pretty easy and straightforward for you to be able to look at. So let's start with those. So 10 to the exponent 4, 10 times 10 times 10 times 10. That's 10,000. 10 to the exponent 3. 10 times 10 times 10, or 10 to the exponent 3 on your calculator, will give you 1,000. 10 squared, 10 times 10 is 100. 10 to the exponent 1. We know that an exponent 1 doesn't do anything. The base just stays the same. So what is our pattern here? What are we doing each step to get to the next thing? Hopefully you see that each time I'm not going down by a common amount. I can't say, oh, it's minus this much, because it's not. It's changing every time. But there's not an adding or subtracting pattern, but there is a dividing pattern. And do you see here that each time we go down in this table, we're actually dividing by 10. So if I were to do that one more time, what do you think we would get for 10 to the exponent 0 in this row? If I take this 10 and divide by 10, 10 divided by 10 gives me 1. Okay, so that's what 10 to the exponent 0 is. What about 10 to an exponent -1? We can do this again. Divide that by 10. What's 1 divided by 10? You can use your calculators. See what that is. I get 0.1. So we're going into the decimals here. Okay, keep the pattern going, 0.1, and divide that by 10. 0.1 divided by 10 is 0.01. So that's a kind of interesting pattern. I see that going down in exponents got me smaller and smaller numbers with the positives, like fewer and fewer zeros. Now with the negative exponents, I'm actually going into the decimal side. And divide that by 10 one last time, I get a smaller and smaller decimal, so 0.001. And this interesting pattern is what we're going to use to be able to represent very, very tiny numbers without having to write out a whole bunch of zeros before the number itself. So for instance, like 0.0000004, we are going to be able to write that as 4 times 10 to some exponent. And let's think about what exponent that might be, because we want to know how many times, like a -1 shifts this decimal. It's one number after the decimal place. An exponent -2 has 2 numbers after the decimal place. An exponent -3, we've got 3 steps after the decimal place. So let's take a look at this one. We've got 1, 2, 3, 4, 5, 6, 7. So that exponent on my 10 for this one would be -7. And that's scientific notation for really, really small measurements. So for these ones, if we're converting to scientific notation, we just have to realize that if you're going into very, very small numbers, that you're going to have a negative exponent. And then it works very similar to the big numbers. We just count how many steps we move that decimal. So here, 1, 2, 3, 4, 5, 6, 7, 8. And then I want the decimal just after the first digit. So this would be 4.56, always times 10, and then we have to figure out the exponent. It's going to be negative for sure because I'm going into the small decimals, and it took 8 steps to get to there. So that would be -8. You guys can pause this and try B and C, and then unpause to check your answers. Okay, so the next one, showing my steps, I'm kind of walking this decimal point back. 1, 2, 3, 4, 5, 6. As soon as I get past one of the numbers that's not a 0, I stop my decimal point. And I saw that that took 6 steps. So this will be 1.347 times 10 to the -6. And then the next one, let's count how many steps. 1, 2, 3, 4, 5. As soon as you get past one digit that's not a 0, you stop. 1.043 times 10, and that was only 5 steps, so to the -5. So it works really, really similar to the big numbers, representing them with these powers of 10. But instead of not having to write out like 30 zeros after the number, you're not having to write out a whole bunch of zeros before the number because it's a very small decimal. So we can convert the other way as well. We can convert from scientific notation into standard form. And just you have to note that if you've got a negative in your exponent, that you're going to make that a really small number and kind of move that decimal to the left because it's going to be a little decimal number, not a big number with zeros at the end. So here I've got 8, 1, 2. I'm just kind of put those numbers there. And then I see I have to move this decimal 6 times. So it started here between the 8 and the 1. I'll move it 1, 2, 3, 4, 5, 6. And that's where the new decimal would go. And I could put a 0 before that too. So it would be 0.000. So 1, 2, 3, 4, 5. 8, 1, 2. And you can double check, is that 8 steps? 1, 2, 3, 4, 5. Whoops, sorry, not 8, 6 steps. 1, 2, 3, 4, 5, 6 to go back to where it started. Now the next one, 3.75 times 10 to the exponent negative 11. So I'm going to put a 375 here, and I have to move my decimal place 11 times. So that's going to move once to get past the 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more times. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, and then the 375. And you can double check as well with counting these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that gets me back to where I was before. Just kind of be careful. Take this nice and slow when you're trying to count those digits. And the last one, this is not so far. It's just a negative 5. I'm putting my numbers there. And then I go 1, 2, 3, 4, 5. So I'll need 4 zeros as a placeholder. So 0.000073. And again, double checking. If you move it 5 steps, 1, 2, 3, 4, 5, does it get back to where it was? And yes, it does. So here's a word problem, and this one kind of illustrates how we can use scientific notation, sort of similarly to what we did with our exponent rules earlier in the unit, to solve problems involving really, really gigantic numbers that would be too big to use our calculators for. So here, this problem says light takes approximately this many light years, 3.2 times 10 to the 7. So that would have 7 kind of more decimal places added on to reach the M31 galaxy and constellation of Andromeda. Light travels about this many kilometers per year, 9.5 times 10 to the 12. Estimate how far away that galaxy is. So for this, you're going to need to know that distance equals speed times time. And I think that that makes sense to a lot of people in sort of straightforward real life scenarios. But sometimes when you get big numbers like this, it can be harder to picture. But if I said, oh, you're jogging at 5 kilometers per hour and you jogged for 2 hours, how far did you go? I think everybody would be able to say, oh, I would go 10 kilometers. Or if I said your family was driving on the highway and you were driving 100 kilometers per hour and you drove for 4 hours, how far would you go? You drove 400 kilometers because you do the 100 times 4 hours. So that's what we're kind of doing. But we have to figure out which thing each of these numbers is. So light takes this many years. That's our time. It takes, not light years, just years to reach that galaxy. So it takes like millions of years to get to this galaxy from Earth. And this is the speed of light. So we're going to use the formula distance equals speed times time. So distance equals speed times time, because it says how far. So I'm looking for my distance. So here we've got our speed is 9.5 times 10 to the exponent 12 times time, which is 3.2 times 10 to the exponent 7. Now, do you see something here that looks similar to what we did with our exponent rules? I've got 10 to the exponent 12 and 10 to the exponent 7. What do we know about multiplying if we have powers with the same base? I know that I can just keep those bases the same and do what with the exponents? The 12 and the 7? I can keep the base the same and add the exponents. And the coefficients, the number parts, the 9.5 and 3.2, we just multiply normally. So that would be 30.4 times 10 to the 19, and that's years. If we had tried to write these out with all the zeros in these numbers and use a calculator, it would not fit in our calculator's memory. It wouldn't show on our calculator's screen. But we can actually do this math. We can say, oh, it's this, that many zeros would be after it and that many zeros. And when you multiply them, you'd have 19 zeros after the product of those two numbers. One more word problem with this. So an average human cell is about 4 times 10 to the negative 9 centimeters cubed. So that's really tiny. Remember that those negative exponents mean 0.000, lots of zeros before the number. Use this fact to estimate how many cells there are in your hand. So everybody's going to have kind of a different measurement here, but I'm going to draw a probably bad picture of a hand. And I want you to estimate, measure how many centimeters do you think your hand is? I feel like my hand might be about 8. No, more than that if I go from the end of my wrist. Maybe 13 centimeters there. And I'm going to say 6 centimeters that way. And the height, I'm going to maybe say 1.5 centimeters. So what's the volume of my hand? About. If my hand was a rectangular prism, which it is not, but if we kind of ballpark it like that, 13, 6, and 1.5. So here, if I multiplied that, 13 times 6 times 1.5, 113 centimeters cubed? Sure, that's kind of reasonable. Now, if I said, okay, now my volume is 113 centimeters cubed, I'm going to write this in scientific notation and make it 1.13 times 10 squared centimeters cubed. If you want to know how how many of something fit into something. This is kind of like the candy question on your Unit 3 test. There was one, and there was definitely some in the homework, that said, oh, okay, if the volume of this container, whatever, some kind of container, had a volume here, and each thing inside had a certain volume, how many could fit? And we would do the total divided by the size of the items. So total volume divided by the size of each item, and that would give us how many could fit inside. And that's what we're going to do here. So how many is going to be the total volume. So I'm going to say 1.13 times 10 squared divided by the size of each cell. I don't know if you guys have looked at cells in microscopes in science yet, but it's a really interesting thing. They're super teeny tiny. So this will be 4 times 10 to the negative 9. I'm going to divide those. Now, this looks like my power rules. What's the rules with dividing powers with the same base? Remember, we're going to keep the base the same. And what do I do with the exponents? Be careful here with your subtraction. 2 minus negative 9. We subtract exponents, but that's actually 2 plus 9, isn't it? That minus and negative, be really careful there. So that would be the exponent 11. And then we would divide the numbers just like normal. 1.13 divided by 4, I get 0.2825, or just 0.28 would be fine. So, but there would be 0.828 times 10 to the 11 cells in just your hand. That's a lot of cells, because remember, that means like that's the number of zeros after this. Okay, so different applications of scientific notation and a really good way to represent big or small numbers. The last example I wanted to do was just to highlight for you about compound interest. We've used this formula before. This is something that we looked at in the start of the unit, right at the very beginning. And just kind of a note, highlight in your notes, you do have that formula and you do have the information about what each of those items is. So the ending amount of money, the starting amount of money, the interest rate, and the number of times you get paid interest. So here we've got different values. Just going to write out my equation. So Sanjean invests $5,700 into a mutual fund. The fund earns 9.8% interest per year. How much will he have first after 5 years and second after 30 years? So I'll do the first calculation with you guys. I'm looking for how much he will have at the end. P, that's the starting amount of money. So that's his $5,700 that he invests in the beginning. The I is my interest rate. That's 9.8%, but I have to make it a decimal. So we would divide that by 100. 9.8 divided by 100 is 0.098. And N is how many years. So here for A, it's going to be 5. And again, this is mostly just practice. Can you deal with exponents and be able to calculate them? So 1 plus 0.098 to the exponent 5. So on your calculator, can you put that all in? And you should be able to do it in one step. And remember, we're dealing with money, so we'll round it off to the nearest 2 decimals, so cents. And I get that he would have $9,096, and that'll round up to 76 cents after 5 years. So I'd like you guys to pause this, try the second one for 30 years, and see what you get. Okay, and I'll go through this again, just confirming your calculations. The only thing that's really changing here is the n value. So I'm going to put in all my numbers again, 5,700, 1 plus 0.098, and now the exponent is 30. So 5,700 times 1.098 to the exponent 30. So on your calculator, make sure you can do that. 94,000, so much more money. $177.04. So we make so much more money in a longer time. And remember, we talked about this with the graphs, that compound interest would start growing more and more, and it would get steeper and steeper, a bigger difference between a linear shape as time went on. So it makes more difference to have investments in the bank or in an investment for a longer period of time.